The title of this presentation is For Triangular Ice to the Ashkin-Teller Model on the Triangular Lattice. To begin with the presentation overview, we'll be discussing some topics that were discussed in overviews and focuses of previous presentations in this series, in which we wanted to provide more details for the three-dimensional quantum inverse scattering type approach, and to add on to general descriptions that were provided in earlier parts of the series, beginning from the discussions in integrable probability that we began the series with. We were providing information to address the following questions for making further connections between the two and three-dimensional approaches, which are related to knowing how many terms appear from entries of the transfer matrix that one must approximate with the Poisson bracket, and also how is the three-dimensional transfer matrix defined, and relatedly, how is the three-dimensional quantum monodrome introduced in this presentation in the series. And then we were also interested in looking at how do computations with the L operator that are expressed in the Pauli basis from the two-dimensional setting transfer to the L operators in the three-dimensional setting. And additionally, we further described how algebraic connections from the three-dimensional L operator along the lines of those mentioned in previous parts of the series relate to staggering and inhomogeneities in vertex models. And in previous parts of the series, we discussed from several perspectives of the operator of the type below, which hold up to Dynkin automorphism. And at first, we were discussing some just more general qualities about it and how it relates to the construction of the universal R matrix, which satisfies the Yang-Baxter equation, and how there's a factorization of this universal R matrix into combinatorial objects, which results from assumptions that we enforce on the universal R matrix from representation theory. And even though the universal R matrix in the two-dimensional case, it's established as a function of the two external fields and the different weights of the six-vertex model, we're still able to make connections and meaningful jumps in inferences in the computations that we perform in the two-dimensional case for the types of computations that we first perform with L operators in the three-dimensional case. And we further built on this by discussing that for triangular ice, there can be some notion of Poisson structure from the fact that we can have 81 Poisson brackets, and we can look at several different combinatorially larger space of combinations for interactions between these terms that are given in from entries for arguments in the Poisson bracket. And then we were thinking about how to actually approximate explicitly different types of entries of the Poisson bracket from these 81 relations. And we were also providing information on triangular ice, which as is described in this reference from DiFrancesco, there are a lot of different types of ways to approach the three-dimensional ice model or triangular ice, from the fact that there have been, as he mentions in the overview provided in his paper, there have been different types of papers which have looked at, in some sense, taking three copies of one-dimensional six-vertex models and gluing them together to obtain a representation for three-dimensional ice. And even though we're not going to exactly stay on this triangular ice model for this presentation of the series, it's worth it to actually see that even if we don't know all of the exact details with regards to the Poisson structure and what's the asymptotic approximation and other properties of the quantum monodromy matrix in three dimensions, even with a lot of information that we've been developing in this series for the three-dimensional transfer matrix, we can still already begin to look at the Ashkin-Teller model on the triangular lattice. And in particular, that can help us make use of a similar type of correspondence, such as the correspondence between the color partition function and the double Grothendieck polynomial that's given in the Buchemas and Shrimshaw paper that we had discussed a couple parts ago in the presentation on the series for some algebraic properties of the six-vertex model and how that relates to colored R matrices and coloring of the vertex model more generally. And from the three-dimensional large N limit, the entries of the transfer matrix form a system of Poisson brackets of entries of the transfer matrix of the following form. So like we said, we're just providing as an example relations 19 through 21 from the set of 81 relations, in which we were looking at all of the Poisson brackets within the set of relations for the Poisson structure of triangular ice, which have the C of U term, which is given at the first argument of the Poisson bracket being fixed, and then we iterate over all of the other terms in a three-dimensional generic representation of the three-dimensional transfer matrix with a U prime parameter instead of a U parameter in each one of the entries. And then we can look at the infinite limit for a weak finite volume limit or infinite volume limit of the transfer matrix in the three-dimensional case, which will be dependent upon some homogenization parameter lambda. So we can take all of, just to make some things with notation a little bit easier, but it doesn't really make much of a difference anyways. But we can just take this homogenization parameter to be equal to the two spectral parameters, as well as having other spectral parameters for the degrees of freedom about which we're taking the weak infinite volume limit. And for approximations to the three-dimensional transfer matrix, like we're looking at this matrix product for I and J being from 0 to N or M, we were saying in the end of the last presentation, and even further describing that in a couple presentations prior in the series, how we can turn to the system of Poisson brackets to approximate in the large N asymptotic limit, and how that relates to more global asymptotic properties of the transfer matrix, and how even though we started off with the transfer matrix in the two-dimensional case, having this type of information, it can actually come into play from more the algebraic connections that are given to the six-vertex model in the Ashkin-Teller model over the triangular lattice. And so that further demonstrates how we can continue building upon some notions of different groups of models within statistical mechanics, because a lot of the themes within statistical mechanics in Carter-Parisi-Yang or KPZ universality, it's relating to demonstrating some type of universal fluctuations or exhibiting that, some very, specifically exponents chosen under some very specific assumptions they hold for a class of models. So obviously, we're not trying to make a statement as strong as that in the comparisons between different models of statistical mechanics that we're looking at in this case. Instead, in this case, from these models as a statistical physicist, we try to think about what would be some characteristic and properties which would be easier to initially compare from these models from each other. And if these models share in these similarities, maybe there's some more profound connections that we could investigate later down the road, or for other aspects or other under conditions of these models, if we just have some information already in space or in place about general types of qualities or characteristics of several models. And so the concluding remarks that we give in this part of the presentation for the series were that we were discussing more aspects of the 3D quantum inverse scattering type approach, and we were answering questions about like, how do the terms in the generic 3x3 representation of the transfer matrix relate to the product of L operators? We were introducing the three-dimensional transfer matrix. We talked about the quantum monodomain matrix, which we'll also reiterate later in the presentation very briefly. And we were talking about how the computations with the Poisson bracket, which characterize the two-dimensional or the three-dimensional Poisson structure, how it's related to the L operators in the three-dimensional setting, and that extra and those extra additional algebraic characteristics that the L operator has in 3 dimensions that it really for the most part, it doesn't seem to have it in 2 dimensions. And we were along the lines of these 4 bullet points in the second part here, we were emphasizing 81 relations appearing in computations in 3 dimensions with the QISM type approach in comparison to the 16 relations appearing in computations in 2 dimensions. So there's a really big complexity gap between the total number of terms which are included in the Poisson bracket in the 2-dimensional Poisson structure versus the total number of Poisson brackets included in the set of relations for the 3-dimensional Poisson structure. And the infinite volume limit of the transfer matrix, like we had mentioned in the previous presentation, is proportional to the infinite volume limit of the quantum monodromy matrix, which is to say that because we use entries in the trace from the 3-dimensional transfer matrix to define the 3-dimensional quantum monodromy matrix, the infinite volume weak limit of both of these objects should be proportional to one another and related. And we had also provided an expression for an infinite volume representation of the transfer matrix, which is given by the fact that we can look at the three-dimensional weak infinite volume limit of the transfer matrix by taking the limit as big M goes to positive infinity and big N goes to positive infinity, and we're taking a trace of a product of L operators, like for the reformulated L operator that we had adapted from the reference that we had presented on many presentations earlier in this series, from exercises with the universal R matrix from Booz and colleagues, in which they provide an L operator, which is one of the L operators that they discussed, which holds up to Dink automorphism. So we can incorporate the definition of a reformulation of their L operator amongst the basis of the triangular lattice, the basis elements of the triangular lattice, to take a product of these L operators and then take a trace to define an infinite volume representation of the three-dimensional transfer matrix. And in 2 dimensions, the quantum monodromy matrix takes the following form, and this is also just from the previous presentation, in which we provided an explicit formula for the action of the quantum monodromy matrix map, in which it's given by the pre-image and image space being the same, namely the tensor product of the 2-dimensional complex space with the tensor product of that in the other term in the tensor product is the 2-dimensional complex space raised to the tensor product of n. And so, like we had mentioned in the last presentation, there can just be a different way to define this quantum monodromy matrix map, depending upon whether for the 20 vertex model over the triangular lattice, you're looking to parameterize the weights in terms of these 2 external fields, H and V, which were originally introduced and described as a parameterization for the 6 vertex weight in the paper on the limit shapes of the stochastic 6 vertex model by Keating, Reshetikhin, and Sridhar. And then they drew our attention to the fact that there's a 4x4 dimensional representation of the R matrix, given this parameterization of the weights in terms of the 2 external fields. And but for the L operators in the 3-dimensional case that hold up to Dink automorphism, we had drew the viewer's attention to the fact that in the last presentation of the series, that in the previous one, that there's a very there's we can look at all these terms which appear in the L operator as spanning some type of dictionary, or even generators like for an algebra, because there's a lot of algebraic connections between the 6 vertex model in on the triangular lattice and in 3 dimensions in the 20 vertex model. So it's like all of these vertex models, if you either look at higher dimensional state spaces for the probability measure of the model, you can basically try to rephrase or look at some type of connection between a discrete probability setting as well as a more algebraic representation, theoretic, combinatorial, or geometric setting. And this is given by the fact that we can enforce different staggering and different inhomogeneities of parameters for the 6 vertex and 20 vertex models, and how that relates to individual terms, which are either the complex valued mapping into the unital associative algebra, or other types of features from the Q parameters, which are raised to differential operators. And like we had mentioned also, the 3-dimensional quantum monodromy matrix is given by a very similar expression with the exception that we have 2 products over K and J instead of just 1 product. And it's a higher dimensional state space because we have the 3-dimensional complex space, which is a tensor product with the 3-dimensional complex space, which is raised to the tensor product of n plus n, because this is representing the total number of terms that we're taking in the product of the diagonal matrix with the universal R matrix. And the limit from the previous slide is related to studying asymptotic properties of the 2 limits below it, because we can look at different ways to define a limit, an asymptotic representation for the limiting object that we would want to get from the product of L operators, and how this relates to the 3-dimensional transfer matrix. And we had drawn the viewer's attention to the fact that we can look at this as in terms of taking the limit as big N goes to positive infinity with a product over I, in which we're just varying the I components, or one of the indices, either J or K or I or whatever you want to label it. And then we can also look at the limit as M tends to infinity in the remaining, in another degree of freedom of the triangular lattice. And we can take a product over I of J all the way up to 9 of J. And then this can be the information from these 2 limits as M and N goes to infinity can be stitched somehow or fused together to obtain a type of limit in which we're varying both of the indices which appear in terms in the L operator I or J, J or K, whatever you want to call them, at the same time to obtain some type of weak infinite volume limit representation of the three-dimensional transfer matrix. And so the outcomes that we had listed for this part of the presentation were that we introduce all operators that are manipulated in 3D QISM type approaches. We discuss how specific terms and lower and higher order approximations of the three-dimensional transfer matrix arise. And we establish comparisons with staggering and spectral parameters for the two-dimensional six-vertex model in previous works under domain wall flat or slope boundary conditions. And other assumptions that can be imposed on the six-vertex model, as we had alluded to at the end of the last presentation in this framework, that relate to either colorizing or looking at the existence of an arbitrary number of colors, can be related to mapping to the three-dimensional Ashkin-Teller model, or like we're going to call it, the Ashkin-Teller model on the triangular lattice, so that we can have one model for the six-vertex model, the three-dimensional six-vertex model, and the triangular lattice, as well as the fact that we can compare interactions that are measured in the Ashkin-Teller model on the triangular lattice, so the same lattice for some type of systematic comparison between these two settings. And so I'm going to be drawing a little bit of the viewer's attention to some other material that I've given on the channel, but from a new type of perspective from the triangular ice or 20 vertex model, because previously I was looking at the two-dimensional Ashkin-Teller model for looking at slope boundary conditions in the two-dimensional six vertex model, but there's many types of notions that we can carry over to this other model in setting up statistical mechanics on the triangular lattice. But we can first have some brief idea about the two-dimensional case, because the triangular lattice or the three-dimensional case of the Ashkin-Teller model will have some more complicated characteristics. And so we know from the properties that the six-vertex model probability measure in two dimensions satisfies, which is saying that given some probability measure, we can take increasing events A and B, and we can look at the probability of A intersect B bounded below by the product of these two probabilities, which is given by the FKG inequality. And we can also have the spatial Markov property, which is saying that the conditional probability under the six-vertex probability measure under boundary condition C of some event occurring conditionally upon the fact that H is equal to C on the union of the complement of C of the finite volume, union of the boundary of the finite volume, is just equal to the unconditional probability with this conditioning removed of just the probability of the boundary conditions along the boundary of the finite volume. And there are also other ways to formulate the FKG and CBC or C or SMP properties, like we had mentioned, and that we can take some increasing functions from the set of all height functions of the six-vertex model, which map into the reals. And then we know that if we take under the probability measure under just flat or slope boundary conditions of f of h and g of h occurring where this is the product of two increasing functions, we can just factor in terms of the probability of f and the probability of g of h, as well as the fact that because the expectation is defined as from the base probability measure, this type of inequality also holds an expectation. And this is to say that under sloped or flat boundary conditions, we can establish some type of domination requirements or stochastic domination, in which boundary condition C prime dominating C imply that the probability of f of h under C prime stochastically dominates the probability of f of h under C, which also extends to the expectation under C prime and C boundary conditions. And the same set of properties that the six-vertex measure satisfies from the previous slide also apply to the absolute value of the height function. So this is just showing that the Ashkin-Teller model, it encodes spatial dependencies and properties of connectivity a little bit differently than the six-vertex model is. And the fact that there can be some stretch component of plus or minus phase variables in the Ashkin-Teller model, it raises some different types of implications for how crossing events can be formulated across strips of the square lattice, like how I looked at in a previous project on the logarithmic delocalization of the height function under slope boundary conditions. And we need to make use of these types of properties for the Ashkin-Teller model from a weakening of properties or from stronger sets or conditions and properties that hold for the six vertex model, because marginal versions of these properties only hold for the Ashkin-Teller model. And we can even formulate the FKG absolute value of H and the CBC absolute value of H as two functions, as two conditions which are dependent upon the absolute value of the height function of the six vertex model instead. And on this paper that I've also discussed briefly, that I want to go more into depth now, from a paper from Domenico Pan and several colleagues, they described how the six vertex model's free energy can be analyzed, in which you want to look at the asymptotic behavior as m and n tends to positive infinity, the logarithm of the partition function. And this partition function is dependent upon the torus which has aspect ratios m and n, as well as three isotropic parameters a, b, and c for the six vertex model. And this is providing and reproducing from their paper as one of the figures the conjectured phase diagram, which we had mentioned throughout several parts of the presentation of the series, in which, depending upon your value relative to the threshold of the disorder parameter, whether it's 1 or -1, you can find yourself within several different types of regions of the phase diagram, in which it's either ferroelectric or anti-ferroelectric. And even though the phase diagram is a little bit different, it's really interesting and powerful to be able to make a connection with the Ashkin-Teller model on the triangular lattice that'll be described in another reference that I'll bring forth to the attention of the viewer, and how this relates more to a dichotomy or different phases of behavior, which can either be ferromagnetic or paramagnetic. So by looking at different types of regions of the phase diagram from one model, you can try to see, maybe if you were map into another model of statistical mechanics, what would be the changes to the boundaries or the contours of the phase diagram, and how that could maybe relate to two-dimensional and three-dimensional aspects or definitions or versions of the model. And so the paper reference that we're going to describe to introduce the Ashkin-Teller model on the triangular lattice, and to further play on to one of the themes that I had in mind for this presentation, in which I mentioned to the viewer that we can still be able to make a lot of use of the triangular ice Poisson structure, despite the fact that we didn't approximate all of the Poisson brackets within the relation and obtain some type of asymptotic characterization of the quantum monodromy matrix yet, is that we can look at the Ashkin-Teller model on the triangular lattice from this Monte Carlo type simulation, in which this large group of authors, they provide several insights which connect very easily with the presentations earlier in the series that we gave, in terms of integrability and triangular ice, and how having, as we said, this very limited or naive notion of the form of the products of the entries of L operators, which hold up to Dynkin automorphism, how that can still already allow us to transfer our knowledge to the Ashkin-Teller model in the triangular lattice. So this is given by the fact that in their reference, as we had mentioned, they can look to produce some type of phase diagram, which is either differing in terms of ferromagnetic or paramagnetic, as we had alluded to, from the conjectured phase diagram that's given of the six vertex model in Domenico Pan and colleagues paper. And this is given by the fact that for the phase diagram of the Ashkin-Teller model over the triangular lattice, we can look at plotting the hyperbolic tangent of one coupling constant for one Potts model against the hyperbolic tangent of another coupling constant of a different Potts model. And then we'll have some segmentation from the borders of these curves of the phase diagram, which would either determine whether we're either in a ferromagnetic range or a paramagnetic range. And paramagnetic range means that, our magnet is pretty much, it's messed up. It can no longer conduct or exhibit ferromagnetic qualities properly. And this is very much related, as I'll mention also in another presentation later in the series on synthetic biology and thermodynamics, and how looking to different areas of science can help us make sense of more rigorous type of behavior that we would hope to justify from just having some more general heuristic information about a biological system or a quantum system or other types of theoretical systems in mind, is that this operator formalism, which is shown to being satisfied for holomorphic parafermions as well as bosonic fermions, parafermionic observables from the Beale and Sampow paper, is done relative to the critical point of the two-color Ashkin-Teller model. So it's just demonstrating that even if you look at the triangular lattice or Z2 or Z3 for the Ashkin-Teller model, you can impose additional colors on the sample space and the state space of the model, which will in turn have the effect of producing an entire line of critical points of the Ashkin-Teller model. And in this paper, for operator formalism of discretely holomorphic parafermions, as an extension of a framework from other authors that I cite and describe in this project, we were able to look to make use of some critical points which lie along the line of critical points for the Ashkin-Teller model for establishing favorable types of conditions for discrete holomorphicity. And from the reference that we had provided a couple slides ago for the Ashkin-Teller model over the triangular lattice, this is how the authors define the interactions between spins of the Ashkin-Teller model over the triangular lattice, and how one can either draw connected components of blue or connected components of red, which account for contributions from either one of the Potts models, which we're coupling together over the triangular lattice. So it's very much to say that it's actually pretty straightforward in some circumstances to look for a difference in the lattice for some models of statistical mechanics, because in this case, we're just defining the Potts models over the triangular lattice instead of Z2 to begin with. And then we can actually make the models from the triangular Ashkin-Teller model and the triangular ice from the three-dimensional 20 vertex model from extensions of properties of the 6-vertex model to be able to live on the same lattice, so that, like how we had mentioned, we can form some type of systematic comparison of the interactions that we're measuring, either in the weights from the 20-vertex model from those 20 possible configurations, or the coupling of the Potts models together on the triangular lattice, where, as we demonstrate here, we'll color vertices within the triangular lattice gray if sigma is equal to -1 or tau is equal to -1, where tau and sigma represent different spin configurations which appear on the triangular Ashkin-Teller model, the Ashkin-Teller model over the triangular lattice, as well as the fact that if we color one of the dots half red and half gray, that indicates that sigma is 1, -1, and tau is 1. So that means that, we encounter some type of defect in some areas of the material from one of the spins of one of the Potts models being -1. And then finally, for the configurations in which we draw the innermost vertices of the triangular lattice, either blue or gray, this signifies that we've just encountered a defect in the tau spin instead of in the sigma spin. And the Ashkin-Teller models, like we had alluded to over the triangular lattice, are defined from the fact that we don't color one of the edges red or blue if all of the spins of 4 spins of the 2 Potts models that we're coupling together are the same, or we can occupy one of them red if sigma is equal to sigma j, but tau I is not equal to tau j. Or, as given in the third item, we can color the vertices of the triangular lattice blue if for an occupation of the bond, if sigma I is not equal to sigma j or tau I is equal to tau j. And finally, we can color a bond blue and red if none of the sigma I, sigma j, tau I, or tau j are equal. And this is all related to some type of expression that they provide for the partition function of the Ashkin-Teller model, in which they're looking at contributions from X raised to either the total number of red bonds, the total number of blue bonds, or the total number of red plus blue bonds. So this is very much to show how we had emphasized time and time again throughout the algebraic characteristics that can be related to the colored R matrices and a colored partition function. This is very much exhibiting how the triangular lattice in defining the Ashkin-Teller model on the triangular lattice from these red and blue bonds, or red and blue bonds at the same time, or bonds that aren't blue and red at all, can be factored into 3 contributions into the Ashkin-Teller partition function over the triangular lattice. And from this set of 4 rules that we have for assigning edges either, or, bonds as either red, blue, or red and blue or nothing. This is very much relating to higher spin vertex models, which we don't have time and we haven't really been discussing these types of vertex models throughout the series at all. But it's another class of vertex models, which is somewhat related to what we have been talking about, from the fact that you can assign multiple ingoing edges or either different colors or orientation of edges at each vertex of the model. So this type of assignment of the edges that the authors from this reference of the Ashkin-Teller model on the triangular lattice, it has very much some types of connections with higher spin vertex models, in which you can either look at, as we see here in the fifth state, you can look at a red and blue edge, or just a red edge, or just a blue edge, or you can have red and blue that are incoming to a certain edge. And then you can have one edge be gray, which indicates that it's an uncolored edge from the first row being satisfied for the Ashkin-Teller model over the triangular lattice. And the Ashkin-Teller model from Glassman and Paled's paper was providing also further information on some types of properties or similar properties that we would expect for the Ashkin-Teller model to hold over the triangular lattice, in which over the square lattice, Glassman and Paled provide several very helpful properties and discussions of what the Ashkin-Teller model is and how it relates to the disordered and antiferroelectric phases of the six vertex model. And this is to say that they provide a very similar type of configuration space for the Ashkin-Teller model, in that its sample space consists of 6 configurations, but the faces are either labeled minus or plus, which encodes a different type of notion, a different type of notion of the gradient of the height function of the Ashkin-Teller model. And when I was originally looking at the Ashkin-Teller model over the square lattice, I began our discussion in another presentation on the channel by talking about the fact that the Ashkin-Teller model being mixed is because spins over odd and even faces of the square lattice are defined separately and they're manipulated separately. And the collection of odd and even faces enclosed within a finite volume are dual to each other. And this has a consequence, as we had alluded to earlier in this presentation in the series, that the FKG inequality which holds for the Ashkin-Teller model is weaker than the FKG inequality that holds for the six vertex model, because Ashkin-Teller FKG is dependent upon the marginals of spin configurations, meaning that we can only expect to have all of the spins be constant, or to have all of the spins along the boundary of a finite volume configuration of, say, all the spins along the even faces have to be the same, as well as the fact that all the spins along the odd faces that are incident to the boundary have to be the same. So we have to encode the boundary conditions, which influences the random geometry that we sample from the Ashkin-Teller sample space a little bit differently, because we have to make different use of a weaker notion of the FKG inequality in comparison to the FKG inequality for the six vertex model under flat and slow boundary conditions. And from their paper, they also provide a wide, a pretty, a good size finite volume configuration, which exhibits several types of differences in which how the orientation of the arrows, it can make the height function increment by 1. But the thing is that even as we can see from these two faces that are given in the topmost row of the configuration, even though the height function decreases from 1 to 0 between these two faces, in the Ashkin-Teller configuration, there's a little bit of a different encoding upon the gradient or the height of the function, the change in the height of the function, and namely the fact that the height function decreases because these two faces are still labeled a plus and a plus. So we have to factor in different types of considerations, as well as the marginal properties of the FKG, CBC, and SMP properties from the set of boundary conditions, from the plus boundary conditions that we use for describing crossing probabilities in the Ashkin-Teller model. And so this is just exhibiting, as we had mentioned, the topmost column of the configuration, and how even though there are some faces along which the height function increases or decreases, all of these faces are labeled plus. And we can also more closely examine pieces of the finite volume between the six vertex model and its spin representation in the Ashkin-Teller model, because when we pass to the mixed spin representation from the height function of the six vertex model, we're going to encounter pieces of the finite volume which really make the marginal FKG and the marginal CBC properties of the probability measure for the Ashkin-Teller model are very important to be able to obtain some types of estimates for costs and probabilities in the strips of the score lattice. And more formally, besides the pictorial definitions of the 6-vertex and Ashkin-Teller models, it's just to say that even the two-dimensional Ashkin-Teller model, much like the Ashkin-Teller model, which is defined from the reference that I provided and described for the viewers from the triangular Ashkin-Teller model, it's still very much dependent upon the coupling constants for coupling two POTS models together and defining these interactions through two two-point interactions and one four-point interaction, which are mediated by the respective coupling constants J, U, and J of the POTS of the two POTS models. And from the Hamiltonian, even in the two-dimensional case, we can introduce the probability measure, which pretty much directly aligns with properties and definitions of probability measures and other objects for the Ising model, and as well for the Potts model, which actually exhibits a useful type of connection from the notions of integrability and triangular ice that we've been looking at in several other presentations of the series, and how that ties in with some connections, some more general connections that we mentioned for integrable probability in the first presentation of the series. And so the concluding remarks were that we reviewed aspects of triangular Poisson structure described in the past few presentations of the series, and we introduced the Ashkin-Teller model, which was originally considered in the two-dimensional setting for the logarithmic delocalization of the height function of the 6-vertex model under slope boundary conditions project. And we introduced variants of the Ashkin-Teller model with either discussing an arbitrary number of colors or also looking at how it can be defined over the triangular lattice, which can already provide us with another model that can help us make some types of interpretations in another setting or other interactions of statistical mechanics, even with some fuzzy notions and some type of general notions of the triangular Poisson structure and those set of 81 relations from the Poisson bracket that we have been describing in previous presentations to this presentation in this series. And we motivated connections between two models despite not having all the terms of the system from the Poisson bracket and the Poisson structure in place like we had mentioned. And thanks for watching.